I would like to introduce Kurt Chankaya. He will be speaking of the use of in-transit fuel for GCR shielding. Welcome, Kurt.
Yay! Okay, so it's a bit humbling following someone as scientifically well, as accomplished as Tony, but I want to present something this is outside of my general area of specialty, so I just want to present something to kind of get a conversation going. In summary, bottom line up front, there are high levels of galactic cosmic radiation, or GCRs, that pose a risk to Martian exploration. How much it poses or how much it doesn't pose is a matter of debate, but high GCR levels do elevate astronaut lifetime risks of cancer. How much it does and whether it's acceptable or not is something that, of course, we've heard very strong feelings from Bob Zubrin and so forth. Whether it's a showstopper or not is another discussion, but it is an elevated risk, and are there ways to mitigate it? GCR particles are highly energetic and they're very hard to shield against. That's what makes it hard. You can't just put an aluminum sheet on you or magic paint or something. These things take a lot of material to stop. And most of the GCR doses that you get for a Mars mission comes when you go there and come back. When you're on Mars, you have this great radiation shield called the planet Mars. It knocks it off in half. There is some mitigation from the atmosphere, and so you're actually getting much higher levels during the transit. So I want to throw out an idea of using the fuel that you use for landing on Mars to use for GCR mitigation by somewhat unconventional vehicle configuration. And what we've seen tremendous changes, Bob talked about it this morning, of the drop in launch costs that we've seen with Falcon Heavy, and the ability to pull a lot of material up into space, a lot of fuel and so forth, so maybe some more fuel-intensive architectures will be available in the future. And how might you use that fuel to do something that isn't parasitic in terms of providing radiation shielding? So a little background of GCR radiation, and again, this is not my area of specialty, but from what I understand, they're very high energy ions from deep space. This is not coming from the sun. This is different than the solar radiation storms that we hear about. They're mostly protons. Some are heavier ions. There's a very small number of very high atomic mass, iron and higher. Those are the ones that seem to be the one that create a lot of concern that I could read about online, because they're very heavy, they're very hard to stop, and when they come and smash into your DNA, they're the most likely causes of creating damage and potential cancer. This is a steady low background radiation. This doesn't come around in storms. It's not directional. It's just kind of there in the background all the time. It tends to fluctuate up and down with sunspots, because as the solar wind, which also cycles with sunspots, goes up and down, these are particles. These are charged particles. They're fully ionized, and so they're not. Radiation is sort of a misnomer that goes back to the history of how they were named. But when there's more charged particles coming out of the sun, there's fewer charged particles coming from outside of the solar system. And so they kind of go back and forth. Here down where we are now, we get a lot of shielding from the atmosphere. We have hundreds of miles of atmosphere, about 14.7 or 15 pounds worth of, on every square inch of oxygen and nitrogen above us, as well as a strong magnetic field. And that really cuts down the GCRs to very low levels. So the point is that the energy that they have does make a concern for long-term health effects, but there's a lot of uncertainty, as far as I could tell, on what exactly that means, whether, in terms of how much risk there is and how important that different types of the GCR radiation are. In terms of how they measure it, you hear GCR radiation measured in terms of grays and sieverts. Sieverts or millisieverts is kind of what people talk about the most. Grays is the units of actual energy that you get from the particles coming into your body and being stopped. Joules per kilogram or kilojoules per kilogram is one gray. Sievert is a gray that's multiplied by radiation weighting factor, and that takes into account what people think is the biological risk of these particles coming and hitting you. So as you can see in the table there, a beta particle or so forth has a weighting factor of 1. Neutrons have a different weighting factor that varies depending on their energy. Protons are 2s. And then the bigger heavy stuff starts getting up into 20s. So people think that's a lot more damaging. There's a lot of uncertainty into what these numbers are, and they've changed over time. But there is a general feeling that the HCEs, or high energy, high mass, high atomic number ions, are disproportionate in genetic damage. So there is a lot of uncertainty into how much risk that will create in terms of what you would be exposed to on a mission. And there's a lot of discussion as to whether the low-level radiation levels that you get over a long period of time are going to be the same as studies that involve lots of radiation risk in short periods of time. As an example, a few years ago we had a speaker here who was I believe a radiation oncologist, and he talked about dumping multiple sieverts into patients, way beyond what we're going to ever give a astronaut going to Mars. And they do this for therapeutic purposes. He said if we gave that to the patient all at once, they would die before they'd die before the end of the day. But we give them to that over a period of months, and it's therapeutic, and actually, is used to cure cancer. And so how often you get something and how long it gets makes a huge difference in terms of how the body's able to stop cancer, how our immune system is able to remove it, and so forth. And all of which is under a great deal of uncertainty. No one has ever taken humans out to deep space and done controlled studies on how GCRs create radiation to them. So the actual risk of them has a lot of question marks around it. With that, in terms of, we do know that they do get higher levels than Earth. And if you look on the lower left, you see it's a log scale or semi-log scale of radiation exposure. This came from the RAD, that was the radiation assessment detector that was on the Curiosity rover as it went to Mars and then landed on Mars, and compared to some other levels. And you can see that the GCR levels that we receive at sea level are only a few tenths of a millisievert, and they're several orders of magnitude lower than what you would get from 6 months on the ISS, which is still below, it's above our atmosphere, but below our magnetic sphere. And that would be in the 80, 90 millisieverts for a 6 month stay. The most that we're allowed to give someone, a DOA annual worker limit, is in the tens of sieverts per year. That's what the government feels is safe for someone to be getting at an ongoing basis. Going to Mars exposes you to about 300 millisieverts. Staying there for 500 days exposes you about 300 millisieverts, and then coming back gives you about 300 millisieverts. And this was at solar maxima, so these are relatively lower levels of GCR exposure, but it's about a total of a sievert. And there's a lot of concern among some about whether a full sievert is a good thing to expose someone to or not. Again, we don't have exact knowledge as to whether this is a bugaboo or whether this is in the noise or not, but what I wanted to throw out is an idea of whether we could use some shielding to reduce the risk somewhat along the way. And the problem is that GCRs are very energetic, so it takes a lot of shielding to stop that. On the right, you see a plot. This is a prediction done by Hassler, who was the author of the paper from taking the data from the RAD, where he looked at the number of millisieverts per year that would be exposed versus soil depth on Mars. And you can see a very typical trend that for GCR exposure where it goes up as you go through a small layer. In other words, being 5 or 10 centimeters under the top of the soil actually increases your exposure, because as these high energy ions come in, they start shattering atoms and they give secondary sprays of neutrons and protons that actually increase the radiation level. In fact, in some ways, one of the worst things to be behind is a thin layer of aluminum or steel. It actually makes the radiation level higher. Other materials such as carbon and certain composites actually seem to mitigate that, but actually having a little bit of shielding can be worse than having no shielding at all. As it goes down to about a meter, or about 120 grams per centimeter squared, you're under about 65% reduction, and about 2 orders of magnitude reduction under 2 meters. So if you're going to build a permanent settlement, we've talked about caves, caverns, and being in underground shelters, a couple of meters really drops it down to the level about where we would expect to be under current Earth levels at the higher end of what we're allowed to be exposed to. As contrast, the Earth atmosphere is 1,000 grams per centimeter squared, and that's even counting our Van Allen belts and the magnetic field around the Earth. So you can tell that a little bit of shielding is bad. A moderate amount of shielding can do quite a bit, and it's going to take a lot to get us around to Earth levels. So if we go on and look at what we might do for a future Mars mission, one of the things that's that has really changed the game, I think, and I don't think we've all quite soaked in what mission architectures are going to look like with low-cost access to space that's coming around from SpaceX and Blue Origin and other folks. But the concept that that weight in low Earth orbit is an unbelievably precious thing to be minimized, may need to be dialed back a little bit. The other thing is that it's very hard to land very heavy things on Mars. Right now, we're landing about 1 ton on Mars, and that's about the technological limit of what we can do with a pure, a standard aeroshell, heat shield, and supersonic parachute. And to get bigger than that, we're going to have to get more creative. We had the Mars Decelerator, which is a big inflatable chute and so forth. But what SpaceX is proposing is a pure propulsive deceleration, pure propulsive landing, in which you just, fuel's cheap. I can haul a lot of it up into space. I'll just haul a lot of it there, and I'll just point the rockets backwards and land. And at that point, you're pretty much liberated to landing whatever weight you want. So looking at my little illustration here, you start off with a fully fueled ship, and you burst into your interplanetary Earth escape velocity, and you're in interplanetary orbit, and you still have quite a bit of fuel on you. And so you take that, and the point is that your outboard transit is while you're still partially fueled. And so you use that fuel to land, decelerate into either into orbit and then land, or you do it into a direct landing, and you land pretty empty. Now, whether you do a Mars Direct mission where you land with one vessel and you return with the other, or whether you refuel the vessel that you came with, it's not necessarily, it's not germane to this particular talk, but you could do it either way. The point is that once you're there, you refuel it, and you come back up, and then you take off again and you return empty. And so the point is that the transit to Mars is while you're still in a fueled vehicle, or partially fueled vehicle. So how partial is partial? So we're going back here. So I took delta V's that you can find for moving around the different parts of the solar system, and the delta V from going from an interplanetary orbit from Earth escape to on the surface of Mars adds up to about a little over 6 kilometers a second. Not an exact number, don't use this number for navigation. It'll vary depending on the different, how the orbits line up and how you do your particular architecture, but something on the order of this many kilometers a second to get you down to the surface. Using an ISP for methane, liquid methane, and oxygen, 370s in the medium range of what I've seen for vacuum cryogenic engines using methane. And that gives you a mass ratio of about a little over 5, or 5.4, which means to land 1 pound, you'd have to start with about 5.5 pounds. And so most of it is going to be fuel. You'll have quite a bit of fuel with you. So if you look here, what that means is if I'm going to land, say, a 50,000 pound spacecraft, I'd need over 100 tons of fuel. And that yields to about 4,000 cubic feet. And so if you took a different geometry to the spacecraft, in which case where the living quarters were inside the fuel tank and had the fuel tank surround them, sort of like living inside a big thermos bottle, you would have about, the moderate size, relatively small, but moderate sized living quarter, you'd have about 1 meter of fuel around you. This would be, an oxygen and methane. In which case you'd have about 80 to 84 grams per centimeter squared of material. And this would actually scale well with increasing sizes because of the square cube law. If I move up in size, I go up by the cube, but the areas go up by the square. So a larger spacecraft would actually have a thicker shield. So trying to guesstimate what radiation shielding that would produce, I couldn't find specific shielding material data on mixture of methane and oxygen, but the Department of Energy did do some work and published a paper on GCR shielding, or galactic cosmic radiation reductions, through up to 1 meter of different materials, including water. And water was the closest thing that I could find to the fuel mixture we had. It's a moderate Z material, moderate atomic number material that's hydrogen rich. And so if we go through about 1 meter of water, it's predicted to drop, here you see neutrons dropping about 3/4 to 2/3 And you scale that for our 1.07 meters, it averages to around 70%. We're a little bit lighter with methane and oxygen. So if you use the weight per centimeter squared, you get a slightly lower number. If you use the distance, you get a slightly higher number. And so using something about 70% reduction on your outboard leg, that would end up being about a 24% total emission reduction in radiation. Last year, I put out an idea of using frozen CO2 as an igloo around an inflatable ground habitat as a way of reducing radiation on the surface. And that was calculated to reduce the radiation, as you can see, from about 320 to, if you stayed inside, all the time, to about 60 by about 80%. And that would reduce the total radiation during the entire mission to about half. So you could say, part of the problems with a issue like this is that I am inside a relatively cold, I'm surrounded by a cryogenic fuel, and I don't like to be at cryogenic speed, temperatures, and the fuel doesn't like to be at living quarter temperatures. So I got to have an insulation between them. And if you calculate the living quarters being at around 300 degrees Kelvin, which is, moderate room temperature, and the fuel staying at around 100 Kelvin, there's actually, that means that the fuel would have to be at a slightly higher pressure than atmospheric, because oxygen and methane don't like to be in the same state, both like to be at a liquid state at 1 atmosphere at the same temperature. But if you raise the pressure a little bit and keep it at around 100 degrees Kelvin, you got a pretty strong temperature difference, but fortunately you're in the middle of what is an extremely good insulator, which is a hard vacuum of space. If you put a few radiation barriers, your temperature change is going to be basically due to convection. We'll have zero convection. It'll have some conduction on the structure that attaches the whole thing together. But if we ignore that and just look at the radiation heat load from the living quarters and assume that you have a few radiation shields that are made out of shiny aluminum, and that the surface of the living quarters and the inner surface of the fuel tank are nice and shiny aluminum, then it drops to about 8 watts per meter squared, and that's about a total of a little bit under 500 watts of heat load for the entire living quarters, which, since it's cryogenic, to keep the fuel down at 100 degrees, it's going to take a lot more than 500 watts of electrical power. Probably takes several times that. But it's a significant but manageable load, and it's certainly a lot less than some of the more far-out ideas of having giant magnetic fields that surround you with multiple Teslas, and that's why I asked the question this morning as to whether what were the biological risks of having an extremely intense magnetic field around humans. This is a much easier engineering solution than some of those more exotic ones. It's obviously not as easy as just not having any mitigation from it and just going without any protection at all. There are other factors about living inside a little fuel tank. It's going to be a little small. There are also going to be issues with being able to see out. But I think that we're seeing a lot of technology in virtual reality, and helmet displays move forward. We can do a lot of things without having to see directly. We can fly planes without having to see them directly. We can operate robotics and so forth. And so the fact that I'm inside a thermos bottle doesn't necessarily mean that I can't, for example, land the plane or land the ship or something. I would be able to do that through electronic means. There are some human factors. People say they like to see windows. During your transit into space, there's really not a lot to see through a window. You could have, nowadays it'd be very easy to put up a number of TV displays to show whatever you want. I've kind of noticed when I came around the airplane that when I was flying along 2 or 3 years ago, I always got window seats because you throw up the window and you can see outside. And then about a year ago, the culture changed, and everybody wants to have all the windows shut And they don't want to see outside anymore because they want to all watch their little iPads or computers or whatever. And nobody wants to see outside. You open it up and you get all these dirty looks from people. It's like, you know, you're spoiling my, you know, my Seinfeld rerun or whatever. And so, so I don't think that being able to see physically out of sight, line of sight, is as big a deal as it might be in the past. I'd like to bring up the historical analogy of the LEM, which of course did have a direct line of sight, but it had its own revolutionarily different position. It was built by aircraft designers. It was built by Grumman fighter plane designers, and they were struggling for a long time how to build a configuration to have someone land and not be enormously huge while they were sitting there. And so until someone said, why do they need to sit? Why can't they stand? You don't stand in an airplane. That's not done. And then they said, well, what if we do it? And the whole thing shrank and became a doable system. And of course, that's what flew. So it just takes a different way of kind of looking at things. So as a summary, fast and sweet, the idea is that can a fuel-intensive mission architecture produce, it would have enough fuel that I could have a relatively thick layer of cryogenic fuel if I decided to put the living quarters and the astronauts' quarters inside the fuel tank without it being parasitic. I'm not dragging around a meter thick layer of stuff just because I want to insulate myself from radiation. I'm carrying it because I'm going to use it. And I'm going to use it right at the end of the mission so it doesn't really cause any trouble for me to carry it with me. Can that produce significant amounts of shielding that produces an increased safety to the crew? That is something that, to echo Tony's conversation, needs research and needs some more investigation. But the little bit of research I was able to do seemed to show that it could produce tens of % reduction in the total GCR level, not enormously dramatic, but not totally insignificant. It does require a different shape to the cruise quarter, it does require a novel approach to human factors, and it does require a higher but I think manageable change to the heat load that would be exposed to the fuel. So that was it. Short and sweet, and see if there's any questions. Do we wait for the mic, or do we just shout out?
Who has a question? Ah, way over there. Speed of light. Yep.
Get some exercise.
I understand that the some of the reaction wheels on some of our recent satellites have been modified to use ceramic instead of steel because as the solar winds would come by, it would cause sparking between the steel bearings, and this would cause pitting and erosion. Would there be much threat of the solar winds causing sparking between the fuel and your oxidizer in the aluminum? And maybe carbon fiber might be a better option to prevent that. I think aluminum does conduct enough that it might generate a little arc and warm up your astronauts very quickly.
Well, it would be unlikely that a lot of solar wind would get through a meter of cryogenic fuel, especially very hydrogen rich. There's a lot of methane there. The other problem is that you're relying on the reflectivity of the aluminum. And it's the high reflectivity that reduces the thermal load. So, I think it would be hard to use a graphite in that application.
Yeah, just wondering if you're able to get any information for radiation exposure from the Navy's nuclear program at all?
No, I wasn't. There's a lot of different data on a lot of different types of radiation, and nobody's done it with high energy, low levels of long-term exposure to high energy, fully ionized heavy particles, which is what they're worried about. And so you find someone says, well, this guy was, 5 miles from the center of Hiroshima. Well, that's a different kind of exposure, you know, and look at radiation levels like that, or radiation, cancer rates from people that have been through radiation therapy, which there is a increased number of people who get radiation after they've taken radiation therapy. But it's a different type of radiation. It's, you know, this is not actually radiation. This is high energy ions. And so I'm not familiar with that specific work, but what my understanding is that we don't really have a lot of really good information on what we're actually worried about here. So.
Any further questions? All right, well, thank you very much.
All right, thank you.